Okay, let's keep going. So, so far we've learned arithmetic sequences. Sequence is a list of numbers that follow a certain pattern. When you talk about arithmetic, you always want to know the first term. You want to know the constant difference, and then we have a formula to find it with a recursive equation and with an explicit equation. Then we learned geometric sequences. Geometric sequences, again, you have a first term, but you have a constant ratio that is multiplying each term to produce the next term. We looked at end behavior. When we learned end behavior, we learned about limits. We only look at them as far as we go out to infinity because that's the way sequences go. You'll learn limits to negative infinity and even to certain numbers next year. Then we learned series. This is the sum of a sequence. On your card, you have several S sub n's. The ones on the left column are for arithmetics, the sum of arithmetic sequences, aka arithmetic series. The ones on the right are for geometric series, which is the sum of a geometric sequence. So if it's on your card and it has a capital S, then it's a series, the sum of terms in a sequence. Thus, the first formula on each column, in each column, on the top of your card is the explicit formula for the sequence. Last time we talked about how much a loan costs. That was just a quick calculation using one of two formulas, both with the same result. And they help you calculate monthly payment, or if you know your monthly payment, your interest rate, or the time of your loan, or how much you could borrow. Pardon my yawn. Okay, so here is 7 infinite series, and let's go to that. So we've had all these ball bouncing problems, and we've talked about, well, how far is the ball bounced if it bounces 6 times or 7 times or 8 times. But generally, when you drop a ball from a certain height, unless you're playing some kind of sport and therefore it gets caught or hit, it's going to keep going. So if you drop the ball, it keeps going. Theoretically, it keeps bouncing and bouncing and bouncing. Gravity has its toll on it, so it bounces not as high each time. So let's go with some finite series have finite sums. There exists a remarkably simple formula for the sum of an infinite geometric series. The idea being, if I drop a ball from a certain height and it bounces back at a fraction of the height, pretty soon you get to pretty small bounces. And then theoretically, even if they keep going forever, how high they bounce is so small it really does not add to the sum of all the bounces. Alright, let's look at what we have. I think I advanced to the wrong slide. Let me find myself really quick. Okay, so you should be able to tell where an infinite series converges. If it does converge, give the limit of the series. Also solve problems involving arithmetic and geometric sequences. We've been doing that all chapter. So we have the formulas like we did before for the first partial sum, which is the first term, the second partial sum, which is the sum of the two numbers, the third partial sum, and so on. Sorry you have to listen to me yawn. Sitting in my living room teaching to no one is not nearly as exciting as being with you all and seeing you when I teach. So, guess what? We have a ball dropped from a height of 12 feet. Here's your 12 feet. The ball drops. It rebounds 3/4 of its original height, so that's going to be, I believe, 9 feet. And then it's going to continue to rebound 3/4, 3/4, 3/4, 3/4, 3/4, 3/4. How far does it travel when it hits the ground for the fourth time? Now remember, this is our first term, this is our second term, our third term, and our fourth term, but it hits the ground 1, 2, 3, 4. So we need the height to go up and down this bounce, and we were using S sub 4 times 2 because the ball goes up and down, minus the original height because it's dropped from that height. So that's 2 times the original height, 12, 1 minus 3/4 to the fourth over 1 minus 3/4 minus 12. Take a moment, figure that in your calculator. I'll pull mine up here. So I'm going to go 2 times, and then I need the numerator by itself, so that's 12 times 1 minus 3/4. Oh, I've got to put a parenthesis in here. And then to the fourth power. Now go past this, close this parenthesis. Now I need to close the numerator parenthesis, and then divide by and start a parenthesis on the bottom, and that's 1 minus 3 divided by 4, close parenthesis, then subtract 12. 53.625. I want to go back and just check my formula because it's easy to make a mistake. Okay, so we have 2 times the whole thing, and then we have the 12, the 1 minus this parenthesis closed to that one, to the fourth, this closed, this parenthesis closed that one, this parenthesis closed the numerator, then we divide by, the denominator is 1 minus 3/4, close, so that 1 minus 3, oh look, yeah, I think I got it, that's the denominator, and I don't have one for all around the whole fraction, I don't think. Yeah, there it is up there. That was my whole numerator. Okay, we're good to go. So I got, for the fourth time, 53.625. Now let's go back to the calculator and let's find it for the 10th time. So I now change my 4 to a 10. Depending on the system your calculator uses, you may have to put insert there. So the next one, after 10 times, it's gone 78.59. Now let's go back into the calculator and hit the 20th time. Second enter brings my last equation down. There's only one thing that changes on each of these. 83.696. 83.696. It's a little redundant, but let's get the 50th time. $83.9999. Notice 4 times 53, 10 times, that's more than double the 4 times, but we added 25 more. Then we doubled the 10 times and we added roughly 5 more. Then we more than doubled it and we really only added not even 3/10, about 3/10 more. So hopefully you see a pattern. Maybe stop the video and look at your results for a minute. I'm going to go ahead and type these out. So 1, well, let me do an extra. Okay, 100th time, 84. So what do you think is going to happen for the 1,000th and the 10,000th time? Oh, let's just punch it in. There's the 1,000th time, 84. How is it no more? So what do you think the 10,000th time? Do we really need to punch it at all? By the time you get to 10,000 bounces, and it's 3/4 the height each time it bounces, there's going to be a pretty small little bounce by the time you get there. So the last, oh, what do you want to say? Not even the last, maybe. In this case, after 50 bounces, no real increase. Okay, so the bounces are small enough they didn't really count. And now you see what's going on here with this. So if there's a limit to a sequence, then see if there's a limit to the partial sums. That's what we just did. We took several partial sums. The series, this is the sum of the terms. If it goes to infinity, it looks like this. The way to find infinity is find the limit of the series. That would be the limit of the sum of the terms of the sequence. So you need to test for convergence of a geometric series. If r is smaller than 1, then r to a power gets smaller as n gets larger. So here in this case, if r is less than 1, when you keep taking it to bigger exponents, this keeps getting smaller. When it's less than 1, it makes the first term smaller. So it gets smaller and smaller and smaller and almost equals 0. So the limit as n goes to infinity of r to the nth power equals 0 for all r that's less than 1. Absolute value of r that's less than 1. The next one, you take the series. Now we want the limit of the series. So we replace the series with its formula. And what happens to the formula here? Well, you have a constant, g sub 1, that should be a 1. G sub 1 is a constant number. 1 minus r is not affected by the n, so they come out. So that is a constant value. And then you put this in here. Well, what happens if you take a number that is smaller than 1 and you take it to a big exponent? The limit goes to 0. So it ends up being 1 minus a very small number, close enough to 0 to say 1. Well, of course, g sub 1, all these typos, g sub 1 times 1 is g sub 1. So we put the most simple formula is for the most complex thought, that the ball keeps bouncing forever, and the formula is simply g sub 1 over 1 minus r. And we're done. So if you need to correct these typos in your notes, or if you need to write it down, whichever you need to do, go right ahead, take care of it, come back to the video, I'm moving on. So you have an infinite geometric series. Here's your sequence. When you're adding them, it becomes a series. G sub 1 can't be 0. If r is between 0 and 1, the sequence converges. You use the formula. If r is greater than 1, the sequences or the terms are getting bigger. Therefore, they don't converge to something. Sorry for yawning. This will be my last lesson of the night. And so there's no limit. The limit does not exist. Straight from Mean Girls. Here it does exist, because r to some power goes to 0. So let's try to find the limit of the series. A ball dropped 12 feet, rebounds 2/3 of the distance from which it fell. How far will it travel before coming to rest? Check this out, how easy it becomes. We again take the series, but now it's an infinite series, times 2 minus our initial g1, so that's 2 times 12 feet over 1 minus 2/3, and then we subtract 12 feet. So that's 2 times 12, 1 minus 2/3 is 1/3, multiplied by the reciprocal, times 3 over 1, and then minus 12. 12 times 3 is 36, times 2 is 72, minus 12, 60 feet. By the way, if you missed this step, it was doing 2 times 12 over 1/3 and then subtracting 12. But instead of dividing by 1/3, we multiplied by its reciprocal, 3. Look how much easier it is when you plug it all in. It keeps bouncing, but eventually it bounces so little that it does not add up to the sum. Here's another one of these. Because of air resistance, the length of each swing of a pendulum is 95% the length of the previous swing. If the first swing is 40 centimeters, by the total distance the pendulum will swing before it comes to rest. So, have you ever been to COSI and you see that thing, it swings this way and it swings this way and it knocks down the little pegs and tells you what time it is? Same idea. Except in this case, there's something going on that what causes one at COSI, by the way, is the rotation of the Earth, which is just crazy. But for us, it does hit some resistance, and so it's going to swing the first time 40 centimeters. Then when it comes back, it's only 95% of that. Then 95% of that, then 95% of that, then 95% of that. Actually, these lines should be right on top of each other, but you'd never see them, so I'm just drawing them lower. And there you go. So, before coming to rest, so infinity. So what happens? It swings, and then it swings, and then it swings. So we don't need to multiply it by 2. because each swing is just a little bit shorter. So we start with 40 centimeters over 1 minus 0.95. That's 40 divided by 0.05. Let's pull up the calculator. 40 divided by 0.05. 800. 800 centimeters. Always label when you can. A hot air balloon rises 80 feet in the first minute of flight. In each succeeding minute, the balloon rises only 90% as high as the previous minute. What's the maximum altitude possible? Turn this off, work it out yourself, and then see what you can, and then see if we have the same answer. I'm going to go ahead and work, but you stop the video, work it on your own. Okay. So that's 1/10. So it's the same thing as 80 times, 80 times 10, or 800 feet. Now, let's watch some language. How high does it rise during the 10th minute? Underline this in your work because that is a sequence question. So we want G sub 10. 60 in the first minute, 80% each other one, and then this is n minus 1, so 9. 60 times 0.8 to the 9th power, 53.4 feet. How high will it be after 10 minutes? So it will have spent 10 minutes in the air. That is a series because we're summing the height of all 10 minutes, not how much it rises during one of those minutes, but how long after the accumulation of 10 minutes. So we're going to go the first term times 1 minus 0.8 to the n, or to the 10th, over 1 minus 0.8. I'm going to go with 60, 1 minus 0.8 to the 10th, 1 minus 0.8 is 0.2, and type that in. $267.79. If you know anything about hot air balloons or the atmosphere, see if a balloon has kind of a ceiling. Oops, I wrote it in the wrong place. See if a hot air balloon has kind of a ceiling of how high it can go. Because now we're going to look at how long it will take to reach 280 feet. So we're going to go 280. That's going to be the accumulation. We don't know this. Instead of writing 1 minus 0.8, I wrote 0.2. Because why? To find this, put this on y1, put this on y2, and let's see what we get. Remember, you always have to use the variable of x on your calculator to graph. Well, I know my x max has to be more than 280. Not sure how long it'll take, but it's going to be more than 10 minutes. So for my window, I think I'll go 0, more than 10 minutes. Let's go 0 to 15 minutes. And let's go our height 0 to 300. Let's see if we can put tick marks every 20. They might run together too much. Not bad. There it is. It finally reached it right there. Where is it? Second, intersect. First curve. It switches to the other one. Second curve. Get pretty close. Hit enter. So it happens at 12.135911 minutes. We'll just drag that one right down here. There we go. Is it convergent or divergent? What's happening to this value as it comes up here? Well, you're right. R is less than 1, so it's getting smaller. Not that quickly, because it's not getting smaller that quickly because 0.8 is a little close to 1, but does eventually level off. So it is convergent. Yes, because R, which equals 0.8, is less than 1. Actually, it's between 0 and 1. What is the maximum height the balloon can possibly reach? There you go. G sub 1, I forgot. 60 and 0.8. 60 over 1 minus 0.8. 60 over 0.2. So here's what I really want to know. Oops, you don't want to see me trying to take my volleyball test there. Okay. So what we really want to know is, try again on the calculator. There it is. Okay, we want to know, would a real air balloon level off and not get any higher? Would it go out of the atmosphere? Would you end up in Oz? Which I'm not even sure. Who's seen the movie The Wizard of Oz? Supposedly he got there by an air balloon. Okay, so 300 should max this out. What percent of its maximum height is it achieved after 10 minutes? So did we calculate it for 10 minutes? We did. 267.79. So 267.79 divided by 300. $267.79 divided by 300. So in the first 10 minutes it had gone almost 90% of its height. So then it just kept going higher, but much, much slower. 263 repeating. So 89%, almost 90%. Which of the following could be convergent geometric series? For those that could be, give the limit. So what's going on here? 5 over 3, 5 over 9, 5 over 27, 5 over 81. Let's figure out what R is. So 5/9. 5/9 divided by 5/9 divided by 5/3 If you're dividing by a fraction, multiply by its reciprocal. 3 goes into 3 once, 3 goes into 9 3 times, 5 goes into 5 once, 5 goes into 5 once, 1 times 1, 1, 3 times 1, 3. R is 1/3. R is smaller than 1, so this converges. What does it converge to? Um, 5/3 over 1 minus 1/3. So that's 5/3 divided by 2/3. 1 minus 1/3 is 2/3. So times 3 over 2. 3 is into 3 once. 5 over 2. 2.5. And I guess we can move this series down here. It did not want to move, did it? I'll do this. Equals 5. Oh, forgot what I wrote. 5/3 times 3 over 1. Then I can erase this. Okay, so what's going on here? Well, let's do 160 divided by 640. So R is 1/4. Because R is 1/4, which is less than 1, so it converges. And then type in 640 divided by 1 minus 1/4, which is 640. 1 minus 1/4 is 3/4. 4/3. $8.53 1/3. When you get 0.3 repeating, generally write it as a fraction. Be more accurate. Okay, 1/2, 5 over 2, 9 over 2. This is getting bigger. You can see that these are getting bigger. So I know that R is greater than 1, therefore diverges. So there's no limit. Somehow I have a whole nother screen of this. So we have the infinite series. We've written this. If R is bigger than 1, it diverges. If R is smaller than 1, it converges. Here are some additional examples. You can stop the video. Let me roll this up a little bit. Stop the video and then work it out and then compare your answers. So you need to know for infinite series, is it convergent or divergent? If R is less than 1 in a geometric series, it's convergent. If R is greater than 1, it diverges. Ask yourself, does it converge? Does a sequence converge? Does a series converge here? So the whole idea, and actually I want to go back to the learning targets to make sure we have those down. Can you tell now whether an infinite series converges? And you know that by looking at, we'll say, looking at R. If it's less than 1, the absolute value of R is less than 1, it converges. Can solve problems with the sequences and then apply those to the series. And that's the key. So each time, let me go to the end and get a blank sheet. So when you're working with these, one of the first things you want to ask is it a sequence or a series? Then you want to say, is it arithmetic or geometric? And there are others, but we are only dealing with arithmetic or geometric. Once you do that, if it's arithmetic, you need to identify the first term in D and N. If it's geometric, you find the first term in R and N, and then you apply one of the formulas on your card. Once you can identify those things, it might be from a sigma, it might be from a word problem, but whatever it is, once you can identify those things, then you should be in pretty good shape. So after you've listened to all these videos, you should be able to complete your homework through 8-7. Chapter 8, sections 1 through 7. The plan is to review on Tuesday and then test on Wednesday. And we'll be doing 8, 6, and 7 in school on Monday, but these recordings are here for you to go back and refer to in case we run out of time or if we need to do homework questions or such. Make sure all homework is done by the review class on Tuesday so we can answer all your questions. Alrighty, that's it. Thanks for listening. See you soon. Bye. Oh no, I may not have been recording.